Hello, welcome back to a new Lötwig Fusel video here in my Borderless 2D game engine series. In this game engine series, we're going to implement a 2D game engine called Borderless 2D. This is video 2. In video 1, we talked about creating the repository, docs, and some weird stuff, basically. So watch the first video if you haven't, if you don't know where we're going to start, because that's going to be important for today. Now, today I want to talk about gluing and igniting. So how to glue go together and how to start up our application. Now, I want to talk first about igniting. So what is static and dynamic initialization, what is hybrid initialization, and what's app-based or instance-based initialization. Then I want to talk about gluing. Why do we need glue if we can build code in one piece? What the mighty preprocessor is doing, and static or dynamic gluing. After that, we're going to talk about a solution that we're going to employ throughout the next videos, which are going to be interfaces, inversion of control, and modules. All right, so let's get started and talk about igniting. So how do we going to kickstart the engine? Now, every application needs initialization. Initialization is a very important thing. If you're writing a business application, a game, it doesn't matter. Every kind of application that you're going to ever write in your whole life requires initialization. And actually, every application, even like your int main that's completely empty, is doing initialization, because behind main is a piece of code written by Microsoft that does initialization. Every time you're going to do and write an application, you're always gonna initialize things. Even if you would have an empty application that does not doing initialization, the operating system is still gonna do initialization for your application. And the BIOS is doing initialization for the operating system, and the operating system's bootloader is doing initializations for the kernel, and the kernel is doing initialization for the more user mode parts of the operating system. So there's so many things that's going on. Everything that we do in the whole world is just initializing some stuff. And yeah, this is why kickstarting and igniting, in this case how I call that, is so important. And it's important that you understand how it works and how to do it properly, especially if you're writing large-scale software than a game engine. Because if you're doing just a small app, it's probably not going to matter. If you're going to call new on every object, if you're going to put it on the stack, it doesn't matter. But if you're writing a big application, the game engine, then you need to take something like that into account. And when we're going to build the system in the next few videos is going to be the fundamental part of the game engine, the lowest level thing that we're going to have. Everything, every object creation is going to be routed through this thing that we're going to build. Because initialization of objects. Now, there are two ways of initialize data in C++, static and dynamic initialization. Static initialization is actually quite simple. Static basically means everything is stateless. You always start with the same thing. And in C++, it actually directly translates to the static keyword. No matter where you use it, if you're using the static keyword in C++ somewhere, it basically means, hey, this is something that shall be statically initialized. I don't care about object orientation. I don't care about runtime initialization when the function starts. This shall be initialized just once at the startup. This is not going to happen automatically. Even static initialization is actually dynamic initialization, but we need to make an exception somewhere, and I'm going to just make the exception where the data is stored. If you are putting something as static, it's stored in some special memory location. It's not on the stack and it's not on the heap. It's in some very special memory location for data. It's allocated when the application starts, because static data, since it's in the code, is always going to be known at compile time. So at compile time, the compiler can specify how big all the static data is, can maybe even provide a complete memory template baked into the exe, how the static memory shall look, and it can bake some code that is initializing the static data. Now, basically, before the main function is called on an application, the operating system calls a static init function that is going to statically initialize the data. It's not actually the operating system, it's actually the code that the Microsoft libraries generate for you. So if you're using MSVC, static init is generated by MSVC. It's some code called before main. And also with static initialization, if you have a class statically, it needs to have its destructor called, which is also generated automatically. So static, in the background, actually dynamic initialization, but I don't care. The general idea is the difference between static and dynamic initialization. Static is going to be there in the initialized state as soon as main is called, while dynamic initialization is initialized later. Everything that you're going to put on the stack Everything that you are going to put on the heap with the new keyword, for example, needs dynamic initialization. This is some code that runs at runtime. The initialization is executed as soon as you get into the statement in the code, not with static initialization. Static initialization, it is going to be there as soon as main starts, which is also bringing us already to the first big problem of static initialization. There's no context. Everything needs to be context and stateless. You can't rely that some other systems have already been initialized if you are using static initialization, which on dynamic initialization you can. If you're using dynamic initialization, you know that static initialization is already done. Or if you're passing like a pointer to it, you know that the pointer is valid and has already been allocated, it is in a good state. You don't get that with the static initialization. Static initialization, which is actually the initialization it's also used for singletons, they are kind of like all initialized without a state. There are ways around that, I'm aware of that, but I don't want to go into too much detail of these because, yeah, in general, static initialization is something you need to be really, really careful. If you have a singleton that's more or less stateless, use it. Put it as static initialize, it's good. However, in general, I do not would recommend it too much, because too much can hurt on static initialization. Now, something that you should be more aware of is something called hybrid initialization. How could hybrid initialization be seen? Well, for example, you could have a static initialized pointer to an object that's then, the first time the static pointer is accessed, gets created, like a singleton. For example, a pattern for a singleton is to have a static function that in itself defines a static singleton pointer, and the pointer is set to null pointer, which means that it's during static initialization, it's initialized to the value of 0, and then dynamically during runtime, you're gonna check if this pointer is 0, then set this pointer to new singleton object. That is kind of like the idea of hybrid initialization. We have something statically, a static state, could be a pointer, could be a whole class, whatever. It's a static state that's floating around that gets dynamically put into the right state if it is like in the not initialized state. Something called hybrid initialization. Now with hybrid initializations and dynamic initializations in general, so dynamic, hybrid, you don't care about what, you are coming to a thing or a consideration that you need to take if something should be app-based or instance-based. What's the difference between app-based and instance-based? App-based is basically, I don't want to say C-style programming, but more or less more similar to C-style programming than instance-based allocation. So basically, or initialization. Instance-based initialization basically means every time you create an instance of something, it's going to get initialized, which basically means it's only suitable for dynamic initialization. Data you put on the stack, data you put on the heap. This is basically instance-based. You allocate that, for example, when the application starts, or if an object is created. It is kind of like instance-based. While something that's app-based is more like a singleton. A singleton with a pointer in it, or a singleton that initializes itself if the values are not matching. So if std vector is empty, do hybrid initialization. App-based, because it's a singleton and only exists once. Now, instance-based seems like normal object-oriented programming. However, it is not. Because consider writing a game engine. On a game engine, you're gonna have app-based initialization. You're gonna have app-based hybrid initialization, for example, for calling co-init on Windows, for initializing the debug layer on DirectX 12, for creating an instance of your implementation or wrapper around the Windows file system. You're doing many, many things that are app-based just for the application, just exist once and always once, no matter how many game instances you might be running in that one process. And you already see where I'm leading. And it's app-based. It's initialized once per process, per user double-clicking the exe. The user might be the developer of the game or the end customer, the end player that plays the game. App-based initialization done in a hybrid way, for example. There is also instance-based initializations, and this is something that is gonna be really, really valuable when we are getting into doing editor and playing in the editor and playing out of the editor with the editor attached. This is instance-based, because basically most of the time, your editor is also using your engine, right? You're going to write a renderer 2D, or we're going to write a renderer 2D, and the renderer 2D might also write an IMGUI renderer. We're going to write multiple renderers for multiple purposes, and every kind of like renderer has kind of like a state associated to it. Now, if we want to kind of like nest these things, right? We want to have one renderer for the editor, and in the editor we have the window where we want to draw the game, and we want to have another instance of the 2D renderer just for that one single window. This might be MID child or MDI child, however this is called in Windows, or it might just render to a texture because it has kind of like a other argument specified during initialization. Really could be anything, but in general, the idea is if you have something instance-based, it can have two instances. However, it is still a singleton. It is a singleton on a instance level. This only makes sense like for like games, right? If you have a game, you kind of like have the process instance and the game instance. If you are on production, you have one process instance, an app instance, and one game instance. It doesn't matter, but on the editor, you might have multiple one of these. You might have the editor instance, you might have the game instance, and you might have a play out of editor instance. So you could end up with three like game instances that all share like one game state. The editor might have a game state for editing the game, while the in-editor play has a duplicated state of that for playing, and also like for like dropping the result afterwards. And out of editor might also have another game state. But all of these shall be decoupled, right? If you have like an in-editor play, we need a different interaction than if we have an out-of-editor play. But all of these kind of like access the same debug layer, which is app-based. And this is something that's really important, especially on complex application like that. Same goes for like if you're writing a web server in C++. You have like app-based, which is like for your whole web server. And you might have instances of that web server if you're running multiple applications. You have an instance of the kind of like transport mechanism that actually handles like sending in and out the packages, doing HTTP translation for the protocol. But you might also have an instance on the per web app base, or even like on a per request base. Well, however, on request, I would say that per request, it's not really a singleton, it's like object oriented. But for a web app, it seems that it is an singleton. However, for the application, it is not. That is the general idea on app-based and instance-based. And this is the main problem that we have to solve here. And this is why I'm doing like all this big talking around. Just because of app-based and instance-based, of having multiple game instances, of being able to duplicate these, of sharing between of these. This is like all code and things that you need to take into account when igniting your application. Because if we now write down all of our code and do all in static initialization, maybe hybrid initialization, at some point this might collapse, because we haven't had in mind that we might have multiple instances of a game on an editor. And then we end up with launching a different process, using inter-process communication frameworks, and whole bunch of madness just to modify their data of some certain state, to copy something over, to have exchange for the logs. This might be something that you want to have actually on a game engine. You might want to have this inter-process or even inter-machine communication. So if you're running it on an Xbox, you can still get like your log output on the PC. But you need to take things like that into consideration, app-based and instance-based. I have a solution for that, and I have a solution how we implement that and how this is like all done. It's only gonna be for singletons. And it's going to be amazing. I promise you it's going to be amazing, but just to kind of like have the awareness here. This is igniting. Igniting is really, really important. Actually, it's initialization, but initialization was such a long word, and igniting is also kind of like nice, right? So it was better fitting for the slides, especially like for that one, right? Initialization wouldn't fit on the text there. That's the idea why I called it igniting. But yeah, let's start and talk about gluing, making sure the right code is compiled and called. This is gluing. So why do we need to glue if we can write an application? Yeah, you can write an application. If you're just using the standard, and if you're really standard conform and writing a non-complex application, there is no need for gluing. Because, well, you don't need to glue something. You just write the code completely standard conform using SCD file system, using if streams, using off streams, using string streams, using SCD string, using standardized libraries that work on all platforms. If you're doing it like that, gluing is not required. You don't need to glue something. If you have debug and release, things are getting a bit more interesting. If we have like we have it debug debug editor, development editor and release. If you have so many multiple configurations, it's getting even more interesting because we actually don't want to have the editor in a release build. We don't want to have the editor in the non-editor builds. We don't want to have our debug and development instrumentalizations in our release builds. We don't want to have debug code in our development or release builds. We have so many kind of like conditions that apply that we need to have a way to glue all of this code together. And how do we do that? With the mighty preprocessor. The preprocessor is the most simple one and most straightforward thing, and the thing that you're going to always use for things like that. You could also use something called conditional compiling to basically say, hey, if you are on Windows, don't compile the source file, right? And then you just have this compiled on Linux or on Windows. And there's also something, I think I didn't mention that, but actually if you're on different platforms, you of course also need, if you're not on the standard and use like DirectX 12, Vulkan and stuff like that, you of course also need to glue these implementations together. On Windows, we glue Vulkan and D3D12 in. On the Xbox, we just glue D3D12 in. On Linux, we just glue Vulkan in. That's kind of like the idea. And how can we do that? Preprocessor. We could also do this with conditional compiling, which is basically what the preprocessor is doing. You could also just completely put out files from a build or have a big if-def around a complete source file to remove that file from being compiled. However, in general, it is always going to resolve to something like preprocessing. Doesn't need to be the C++ preprocessor. We're going to just have it because it's the most simplest way to do it, right? We're always going to have every file available, and we just going to make sure that the preprocessor is called in the right way. Now, what is static and dynamic gluing? Now, static gluing is very, very simple, and what I've just explained. It is just the preprocessor. It's all done statically at compile time. At compile time, we know which pieces of the code are going to get glued in, and it's all linked up statically together. Which is going to be a problem at the example that I've already presented you. For a renderer, we can have on Windows Vulkan and DirectX 12, while on the Xbox we only have DirectX 12, while on Linux we only have Vulkan. So we kind of like have a bit of a problem to glue that in. Xbox, it's not a problem. We just have one renderer, we can wire this one up statically. Linux, we also have only one renderer, we can wire this up statically. However, on Windows, which is our main development platform, we have two options. DirectX 12 and Vulkan. We could create two builds of our application, however, that's not kind of like the solution. We cannot build different applications for every like scenario. It makes sense for something like Steam that we have a different configuration because we need a different exe that gets out of that so that it's compatible with Steam. But everything that's kind of like not dependent of the exe should not have its own configuration, right? We should not have a own configuration for Vulkan and one for DirectX 12. I mean, I think there are games that do that. I think Control, actually, we could try to look at this. This is like my records, and I think if I go to my Games U, Steam Library, Steam Apps, Common, and I go into Control, you can actually see that there's a control.exe, which is basically just a launcher, DX11 and DX12. This is how they have done it. They have done it basically with static gluing. They have an exe for DirectX 11 and they have an exe for DirectX 12. Bad idea. I mean, not too bad. However, I would not recommend. It does work. You can see that it's virtually the same code. They are the same size because basically they are just calling a different rendering API, and I would not even be surprised if the actual code that is running the renderer is actually a DLL. But I'm not quite sure of that, how they do it. It's I don't want to take too much look here at a controller and try to figure out how they have done that. But basically they have done it with static gluing. DX11, DX12. Very simple, very effective, good, but not good enough for me. I want to do it like other games. For example, I think Cyberpunk does it like that. I'm not quite sure of that actually, but I think Cyberpunk does have DirectX 11 support as well. If I went through, I am not 100% sure of that, but I'm just going to pretend Cyberpunk does have DirectX 11 and DirectX 12 support. Then they have a Cyberpunk exe, and this exe is containing both codes. for 11 and for 12, and maybe also for Vulkan, right? So it might have the support for 3 renderers inside of it. But the problem with something like that, called dynamic gluing or dynamic, could also call this dynamic linking. I really don't care about how, but linking is most of the time kind of like concerned like how you link libraries in. Like you have your renderer d3d11 and renderer d3d12.lib, and you either take it as a DLL or either take it as a lib, and then at startup you check at the configuration file and you load the library and you have functions that you import from the library and you can do dynamic linking. But that's not what I want to do. I want to do dynamic gluing and or static gluing. Static gluing, already explained that. Now dynamic gluing. Dynamic gluing is basically the idea of conditionally compiling the modules, and now we're already at the concepts that we're going to use for the engine, that you're going to compile all the modules that are compatible into one big exe, like a Uber exe. Everything is in there. It's all in one big chunk of code. And what you're going to do at runtime is dynamically glue your dependencies together. For example, you're going to have 2 implementations of the renderer 2D. The renderer 2D might have an implementation with DirectX 11, DirectX 12, and Vulkan. And dynamically at runtime, you're going to decide which implementation you're going to take and wire up this pointer to the systems that actually invoke these calls. So you glue the code together dynamically. Previously, it was done statically, like a type def. You just have a different type def and everything is kind of like glued up differently. And now we kind of like have this dynamically. We don't know which implementation is actually used. We have an interface and we are calling that interface. And no matter what API is behind it, it's going to do the job that it was designed for doing. Dynamic gluing, as I have called it. Static, dynamic, very simple concepts, easy. Now let's go to the solutions, how we do it. We do it by using 3 concepts: interfaces, inversion of control, and modules. Let's dive in these without further hesitating, and I think now is the time where I at least should make myself a bit smaller so that you can see what's going on. Alright, so the first concept that we're going to use are APIs, interfaces and implementations. For example, if we want to render something, we might have name's probably going to change, probably going to come up with better concepts, but for now, we just have for rendering the iRenderer context. The iRenderer context is responsible for creating the renderers, like an IMGUI renderer, a debug UI renderer, which is probably the IMGUI renderer, but yeah, I don't care, like a renderer 2D, the IMGUI renderer, and maybe like an overlay renderer that can render simple text like FPS numbers and things like that on the screen, right? We have a renderer context, which is kind of like a factory class that is used to interact with like the D3D12 and Vulkan, right? The iRenderer context might have an initialize function or an enum GPUs, and then you say activate GPU, give it a certain GPU, and then it's activated for that context. Now the context might have different implementations. We're probably going to have DirectX 12 in there, so the D3D12 renderer context, and in the future also maybe the Vulkan renderer context. So there are 2 implementations that implement the features that the iRenderer context describes, like the interface that it's defining, in a different way. The D3D12 renderer context, it internally, if you are on debug, maybe initializes the debug layer. Might be, probably it's not actually. Debug layer is probably going to be a whole different class. It's probably going to be like an iDebug suite API that's going to have multiple implementations, or iGraphics debug suite. I don't know how I really want to do it. Maybe it's also like done in there, but we're going to see how it finally turns out. But the general idea is we have an interface that's API independent, OS independent, which does not reference Windows, which is not referencing DirectX 12. It's just a plain old API, just referencing stuff that we implement in our engine. And the implementations are then allowed to like call the OS, call APIs, or maybe even call other systems, right? If we could have like a iEngine core for development, debug, and release, right? Like we can even do this on our own. We can have 3 different implementations of our core gluing system. And depending on the configurations, we are dynamically compiling one or the other library that might also even build up together on each other, but might not be available on one of these platforms, right? We might have, might say, alright, the core one that's used for release, it's always going to be there. And then on release, we basically just build the platform support for like Steam on top of it. On debug, on development, we build development stuff on that. On debug, we build on top of the development stuff, the debug stuff on there. And we can kind of like even be like building these hierarchically up to each other, and then use static gluing to wire the correct one in. Speaking about wiring the implementations to the interfaces, inversion of control, right? We have a so-called IoC registrations container. The IoC registrations container is gonna basically gonna be a list or an STD unordered map, however we're going to implement that. It's going to be just a container that contains multiple descriptors, right? The descriptor might contain the size of the actual implementation and an STD function to a factory and a deleter. We have a factory function and we have a deleter function. A factory function, well, it calls the constructor, makes sure it's on the correct memory, everything is initialized. The deleter makes sure the destructor is called, right? We have this in here in a descriptor described in a uniform way that is like independent of the implementation, and that kind of like is useful then. And then what we can do is we can talk with the IoC registrations and tell them, hey, give me the singleton of iRenderer context for D3D12. Now I have made one big limitation in here. I have defined that IoC registrations can only be singletons. So if we want to have dynamic initializations of instances, for example, multiple 2D renderers, we always need to go, this is also why I call this renderer context, go over one renderer context. So everything that's kind of like registered in the chain is a static instance, a singleton. And this is the all story about this igniting and gluing, right? We're going to do only static, or it's not static, it's actually hybrid initialization. We're going to do completely hybrid initializations over inversion of control of singletons. And the singletons might then be factories or real singletons, right? Like the Windows file API or file system. They are going to be real singletons and factory that then create the objects for us. And they all gonna be evolving around these APIs and be registered there. And what we can do then, we can say what we want and we can give it a specialization. The specialization is important, right? Because we want to support multiple renderer contexts. On Windows, we have two available, D3D12 and Vulkan. And then later in the config file, there's something like renderer equals, and then you're gonna like give it a name, for example, D3D12 or Vulkan. And at the startup, I'm basically gonna call, hey, IoC registrations, give me templated function iRenderer context template and arguments config get key or get value for key renderer. And then the configuration tells, hey, I want to use that renderer, and the IoC registrations is then ask, hey, come on, I have that API that I want to have for that key. The registration is kind of like mixing that into one key that's then looked up in the descriptor table, and then, well, boom, they find a single descriptor for that, and with the single descriptor we can then go on, and we have the factory function for that. We have the size, so we know how many memory bytes we need to allocate and which function to call to initialize this properly, this piece of memory. And then we have a deleter as soon as we are done, how we can delete this. Talking about deletion, lifetime and application and instance aware instances. Singletons, initialization, instance aware and application aware instances. Well, they are going to go over one uniform concept of a so-called stack. I want to have IoC stacks. An IoC stack is basically a descriptor plus an instance. So we kind of like, as soon as something is requested to be created on a stack, we reference the statically initialized, and it's actually not statically initialized, we're going to see later on how this works. So basically the IoC registrations are statically initialized, the container for them is statically initialized, and then it is dynamically filled, which is making all of that a hybrid initialization, so a hybrid initialized list of the implementations to the matching APIs and specifications. And what we do in an IoC stack, we basically create ourselves an IoC stack and we say, hey, give me that interface with that implementation, and then it's basically going to ask the registrations. Is that registration available? Yes. Give me the descriptor, store the descriptor on the stack, create an instance also on the stack, and go on. And at the end, when an IoC stack is destroyed, it's basically rolled up in the reverse order so that all objects are correctly into the correct order destructed. So construct, destruct, as it works, just a simple concept of a stack. And since it is a class and that it's object oriented, we can have multiple IoC stacks that are dynamically initialized. So we have a static initialized container with dynamic initialized implementations stored in there with the meta information how to create them, which makes kind of like the registrations hybrid initialized. And then we can dynamically initialize a context where these singletons are going to live. And the nice thing about that is that in our main function, we can create one IoC stack for our application context, and we basically then call like a bootstrap method, and we give the bootstrap method the stack, and it's going to initialize all the static application data, and at some point it's going to hit the kind of like initialization done checkpoint, and then we basically create our application instance, and we kind of like give it the static stack and the new stack, and there's going to probably be a feature to chain these stacks together to have kind of like a parent stack, so that we then have on a per like application instance or on a per game instance a stack. And if you are kind of like asking that stack, it's first going to consider its parent stack, and the parent stack, if it can't find something, it is kind of like initialized in the other stack. So we might need to have freezing on there, or kind of like tell it that it's like only shall lookup but not create. There are many, many things that we need to wrap our head around, that we need to see how it grows and how it makes sense to implement them. But this is like the basic concept. All right, let's talk about this one times again. Modules. I've told you that we need to have a way to glue our code together. How do we want to glue code together? We're going to glue code together by defining modules. Now, we're going to have one big project in our Visual Studio solution that's going to define all interfaces. This is going to be one big project, a header-only project, which is going to define all the interfaces, the enums, the struct, everything that the engine needs. One big header-only project. We might have a few helpers in here that are also only header-only, like kind of like our engine standard library. Templated standard library, however you want to call it. One big library that's going to define all interfaces, the whole API of our engine. And that's also going to maybe define a few helpers on how to use the API easier. Maybe we're going to do a static link library that is going to contain all these helpers. I don't know, we are on Agile here, right? Agile is something that everybody talks about. We're going to see where we go. However, after we have these like interfaces, we need to implement them. And for that, we're going to define modules. And every module is going to have a single point of kind of like responsibility, right? We're going to have a D3D12 rendering library. We're going to have a Vulkan rendering library or module. These are going to be libraries later on in code, but yeah, module. We're going to have one module for DirectX 12, for Vulkan, for the Windows file system, for the Linux file system, for the virtual file system, for the virtual emulated file system, which basically means consider this call to be made from a production build, but redirected to the system file system instead, the real file system, so that we don't need the file baking build. But that's also something that we're going to go to as soon as we talk about asset packing and resource management and all of that stuff. So like the general idea is every kind of like specialization of the implementation of a set of APIs, it's going to contain its own one single module. And these modules are compiled conditionally. If we are on Windows, we're not going to compile the Linux modules. If we are on Linux, we don't compile the Windows modules, but we're of course going to always compile the common modules. And the common modules, they're going to use the platform-specific modules, but they don't use them directly. They use them over inversion of control. So they don't really consider them. They just know how the API is. They know where the IoC stack is and ask the IoC stack, hey, on this stack, create me that instance with I like this specification. And everything else is then handled by different modules, and each module is contained in itself. It's having a single like responsibility, and it is simple. That is the most basic idea. Every module shall be as simple as possible, and thus so small as possible, and also be as straightforward and one single purpose as possible. We don't want to have a big implementation on Windows module that contains all Windows code. No, I don't want to have that. I want to have real specializations for every module. Every module shall be simple, and every module shall be understandable, right? Because if I want to learn from that code that I'm going to write, and I just want to learn for my engine how asset packing works, I'm just going to take a look at the module for asset packing. There might be like 3 modules that I need to consider then. There might be or actually not 3 modules, because like the virtual file system is then described in the header-only library. So I know, all right, in the header-only library, there is the API for the virtual file system, or for the file system in general. I understand how a file system works. I take a look on how the virtual file system works, and I take a look then maybe on dependent modules that actually are doing like the virtual file system tools, right? There could be a module virtual file system tools that is defining the the packet format of the virtual file format, what operations are supported on the virtual file container, how maybe asset protection and compression is supported, and then I can take a look on how the implementation is kind of like used in IoC, right? There might be one package for packing, one package for using. And the package for packing or the module for packing is only available in development build, while the consumption of these packets, of the virtual file packets, or file format of the virtual file format is only available in release, right? It's getting a bit complicated to just directly talk about this without having really thought that out completely how I want to do it with the architecture for this special virtual file system case, right? I know how I want to do my modular architecture and my loader and everything, but I haven't like really considered just yet how I want to do my virtual file system. So it's kind of like a bit strange that I am repeating and not seeming 100% sure on how I want to do it. But that's okay, because it's agile. As I already told you, we are today just specifying how initialization and gluing works. And I would have not thought that this video would gonna fill a whole episode. I thought that I at least could do a bit of coding, but nah. But I think it's important that you understand how the concepts are, right? That's important. One example is here on the page. So if our application loads on the main function, we first load the modules. The code that is loading the module has been generated by the preprocessor, because the preprocessor knows, and we're gonna write that code in the next video, because we're gonna write some code in premix, some Lua code, that is basically gonna check, hey, this module is only for Windows, and only if I'm then on a Windows build, it's generating a project for that, and it's generating a macro for that. So a hashtag define, this module is available, kind of like. And what we can do is we can write one big CPP file where we basically just say, if this module is available, this module register, right? And in general, how this works, application starts, main starts, application loads. We're going to call load module generated by the preprocessor, which is going to register the implementations with hybrid initialization, static initialized container, dynamically initialized components in the container. The components in the container are now registered during register implementation, but the kind of like container for that is static. But with load modules, with the registering implementations, we are kind of like defining the hybrid initialization pattern. Now, after that, after all the modules are loaded, we kind of like have the knowledge of which modules are available and which specifications and how they are constructed, how big they are. We have all that metadata available, all these descriptors in the IoC registrations. What we can then do is we can create a stack. And with that stack, we kind of like do dynamic initialization, right? Because the stack is gonna live on the stack. This seems a bit odd, but the stack is gonna live on the stack and have its memory on the heap. That's how it is. But yeah, so we have a stack on the heap. What? Oh, but okay. Virtually every stack is on the heap, but that's a different story, right? No. We create a stack, which is then going to reference all of the singletons using dynamic initialization. Now, as soon as we're then going to try to receive a class A without specifications, it's going to create A with dynamic initialization via these factory methods. This factory method might do code, for example, like retrieving other implementations first. So this might do hopping. So for example, if I create a context, the factory method might first create like a debug context. Right? So it's creating a debug context. This one is initialized. This doesn't depend on anything else. Then the debug context is initialized, returned, and then I can continue on initializing my context, since it's a factory method, with the debugging context plugged into that, because we are on a debug build, glued with preprocessor logic. But still, dynamic initialization via a factory to mimic static initialization. So yeah, interesting thing. And then we can return A. As soon as we try to receive A again, we're going to directly return A, because that's the whole idea. We're going to write igniting initialization gluing code. We want to have a stack for the application and a stack for the instance constructed in the state, so that we can then, on top of that, dynamically handle our engine. That's the whole idea, and that is rocket science? No, it's not. It's actually quite simple, but still 40 minutes of talking head video just for something simple as a game engine. You're going to see that this code is it's going to seem ridiculously short for the amount of time that I am talking about this. But that's the whole idea. Okay, thank you for watching. We're going to see us in the next video. In the next video, we're going to make sure that our build system is going to be compatible with my concepts. And the following video, we're going to make sure to implement the IoC madness and try it out how it works. Thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye.